This is the Sherpa Mini extruder for anybody who's strangely found their way to my channel without having kind of a more advanced knowledge of 3D printers. The extruder is the part of the printer that grabs the filament and pushes it into the hot nozzle to make your prints happen. And this extruder is very lightweight, and that's good because you can make it into a direct drive extruder like what you see here. And direct drive extruders offer superior performance to their Bowden counterparts, but that performance comes at a cost because you get what's called ghosting or ringing in your prints, as the heavy weight of the extruder, mostly the extruder stepper motor, as that is forced to sort of change directions during printing. That causes the printer to vibrate or ring, and the ringing manifests on the walls of the prints as sort of these vertical witness lines. But that's still more desirable than the drawbacks which you get from Bowden tubes, namely lots of stringing and a difficulty with retractions, and yeah, there's some other minor problems associated that direct drive addresses. Still, it's silly to put a direct drive extruder onto a bed slinger or a Mendel style printer like your Ender 3 or your Prusa style printers, because you only want to print as fast as your heaviest axis. And when the bed has all of that mass moving back and forth, your extruder and everything can weigh every bit as much as the bed. So actually, take back what I said a second ago. You do want direct drive extruders on those, but you just don't care about weight because you're already being as slow as the bed is causing the printer to move. So yeah, this kind of an extruder, a lightweight direct drive extruder, is mostly intended for like Core XY machines or similar, where the bed moves very slowly in the Z direction and the X and Y directions both are happening with the nozzle, with the printhead itself. So it's a pretty great thing, and this one certainly seems to be the lightest on the market, at least to my knowledge, but it's not perfect. So let's dissect this thing and figure it out. Okay, first impression of the Sherpa Mini is functionally it's no different than the Superfly, which I reviewed last time, and the Orbiter extruder, which I reviewed a few videos back. And that means that it's just an extruder. Like, there's no hot end attached to it. And it's got these mounting points, and you're meant to figure out your own hot end mount to it. So the whole point of an ultra lightweight extruder design is as a direct drive, right? It can be as heavy as it needs to be if you're going to run it as a Bowden tube. So it's kind of a cheat to just be designing an extruder without considering the hot end component as well. Like, there should be custom mounts for this thing that mount to a Slice Engineering Mosquito, that mount to an E3D V6, that mount to other hot ends out there on the market. And that's going to save weight in the end because there's a flange here. You see this whole flange with these bolts that have to mount to it. So that flange is a significant amount of plastic. Those bolts weigh a lot, and then you got to think that hot end also has to have its own mounting hardware, its own flange, and all of that. So you're gaining a lot of weight that's unnecessary if it was an integrated solution. So it's not the largest gain to be had in this design, and the number one problem in the cognition behind the design is the fact that it's that engineering approach where you divide and conquer. Every team of engineers or every engineer gets his own little task. He does his task to the best of his ability, or she, female engineers too, and they, they work in isolation, and right at the joint between the two teams, you have massive losses in efficiency. So you need to have a whole picture of the product. And with a direct drive extruder, that's really not a hard thing. I mean, a space shuttle, I get it. You got to divide and conquer. But an extruder, come on. Really? You're going to split this up into such minuscule tasks? That doesn't make a lot of sense. All right, let's take this thing apart. Okay, so this is the extruder unit itself. It's skeletonized, nicely done. I really like this. I've got the backing plate pulled off, and the main gear can get pulled out, but only to that point before the involute gear here, the involute gear portion of the hob gear, gets caught on the geometry somewhere inside there. So in order to get this thing apart, I need to take off this front plate, and that means 2 extra bolts and an extra plate, an extra printed piece of geometry. So that's That's a significant amount of complexity added to it. And we know the KISS principle, keep it simple, stupid. And, you know, less is more. There's all kinds of ways of saying this. Elon Musk is recently pretty famous as saying the best part is no part because it doesn't break. It's you don't have to pay for it. Blah blah blah. You know, the best. You should look up that quote. It's a really good quote. So yeah, look at that. I can't get that out. You see that the involute gear right there is catching. Look at the way it was done on the Superfly. That whole gear just slid right down in from this side, and then you put this cap on the backside like so. So that's the way that this should have gone, and we would have lost a significant amount of weight and complexity. 2 of these inserts, this whole cap piece, all of it could have been removed. Oh, I get it now. This whole thing was designed to be printed on an FDM home 3D printer. For that reason, we've got the parts that look the way they look. This cap here has to go on like so and capture the pivot point right there for the filament arm. I don't know what to call this thing. The levered arm that closes the breech on the dual feeding hob gear. So that makes a lot of sense when your constraint for the design is printing FDM. All of these parts, look, this has a flat backside. This has a flat backside. I think you would print this one in this orientation. And so this is clearly designed for FDM, and now it's being printed with SLA, SLS, selective laser sintering, a powdered nylon hit with a laser. In the bed of nylon, you don't have to worry about overhangs. You can print however you want. So this whole thing could have been printed in one go, like so. And you could have had the piece slide into it like that, and then you slide the pin, the pivoting point pin through both elements, and you wouldn't have had any issues printing. So classic. This is classic China. Basically a part designed by a DIYer engineer who looks to be really capable and quite intelligent, and designed for one process, and China just takes it and makes it exactly the same. Carbon copy, and they do the easy innovation. It's not an innovation. they just printed it with an SLS machine and, you know, say it's better. And they should have redesigned. But they don't think about these things in China. They just make. They just, as quickly as they can, get the product onto the market. So this needed to be redesigned the moment that somebody thought that they were going to make it with a different type of 3D printing process. So yeah, lightweight as this is, I think I could drop 50%, not exaggerating, 50% of the weight off of it by designing it for selective laser sintering and also designing it to include an integrated mount for a hot end. But as I've said in previous videos, the weight savings in the plastic extruder portion here is kind of, a lot less important than the potential weight savings in redesigning stepper motors. So this stepper motor here, we've seen it before on the orbiter extruder, and it is a lot smaller and lighter weight than a pancake stepper NEMA 17. Still, I'm seeing the same spacing on the screws. See, diagonal to diagonal. It's the same on both of these. The shafts appear to be the same, and if I hold the circular portion up to the pancake, it looks like this could already be just a lightened version of a pancake stepper motor. So I want to take a look inside of this and compare it to a pancake. But first, let's do a weight comparison. I'm going to do my best to just sort of hold the wires in the air. I don't really want to measure the wires, so yeah, I'm not moving that, but it's not moving very much. So we're looking at about 70 grams. With this one, we have 120 grams. So yeah, like a 50 gram weight savings. Pretty impressive. But that weight savings comes at a cost. Looking at the stator for these two motors, we can see the NEMA 17 is a lot more robust. The windings here using a much finer gauge of wire than this one. I'm going to assume about the same number of wirings. More windings equals more magnetic power, but it's a massive trade-off there because the longer the wire, in other words, more windings equals a longer wire. The longer the wire, the more resistance, which means the more heat. So your smaller wire gets hotter as you apply more power to it. So you can't overclock this thing. You can't just shove more electrons through it to get it to have more torque. Whereas with the NEMA 17 here, you can absolutely feed more current into it and achieve more torque. Taking a look at the two rotors here, we can see just how much larger the NEMA 17 is. It's significant, right? And that means that there's more leverage. The magnets are farther away from the center point of rotation, so each step is going to have more pulling force. So the NEMA 17 is going to be significantly more powerful. And speaking of integrated solutions, you can see I've removed the stator here completely from the housing, and I've got the back housing along with these two screws on the scale weighing 7 grams. This is the back plate of the extruder, which the back plate or front plate of the stepper motor mounts to, just like that. And why couldn't you just integrate these two parts into being a single part there? Well, this is a problem. You see the filament path here? The 1.75 millimeter filament is significantly smaller than the hole, the orifice there. And the orifice is hexagonal. I think that was a design consideration, again, for printing this on FDM printers, where the top being sort of pointed like that would yield higher quality print. But now that it's being printed with SLS, there's really no reason that isn't the correct size. And also, it should have just been, if I had designed this, it would have just been a 2 millimeter hole the whole way through. I think my solution is going to be to drill that out to 4 millimeters and slide a little piece of Bowden tube PTFE liner down inside of there so that we don't have that wiggle room. And the wiggle room is really substantial, and it's really important because if you're printing with flexible materials, you need to constrain the filament path tightly the entire way after the hob gear. Speaking of which, I understand why this gear now sits the way that it sits, where you can't pull it out with the main big gear. You have to unscrew it from the shaft and take it out the front. And the reason for that is because the filament path right there, you can see the little pointy bits of the plastic to meet with the hob gear. They're nice and tight right around that hob gear, and the teeth of the involute gear stick out proud of the surface of the hob gear. So you can't get it. So the only way to get that to be able to slide out the front with the main gear there is to make the tolerance less tight around the hob gear. So that's the filament path tolerances are nice and tight. That's a really good consideration. So I would not change that design. Okay, this drill bit measures 3.96 millimeters, so real close to 4 millimeters, and it's a friction fit. It'll slide right in there. So that tells me if I can get good enough grip onto this PTFE liner, I should be able to shove it up inside there. And yeah, so I didn't need to drill that out after all. And my trick for getting grip on PTFE tube is to use some sandpaper and just push it on in. And then you'll typically want to chase the hole with a 2 millimeter drill bit just to make sure you have enough clearance in there for the filament. The final thing to say about this before I go to work making the adapter plate and putting the hot end on there is that an opportunity was missed to have the gear sitting proud and exposed so that I could grab it with my thumb and feed the filament through. See if I use the, you can see if I use the screwdriver right there, I can get the filament to inch out. But as it sits right now, the only way is to kind of loosen this, and this is pretty loose, and that door is pretty much there. And even still, I'm fighting with the hob gears. So it would have been really nice to be able to manually push that through. Oh, by the way, 122 grams on the Sherpa Mini here. The previous weight weenie, the winner for weight here was 148 grams with the orbiter, but if we take off this unnecessary bit of heaviness, 142 grams. So 20 grams heavier, which is about the weight of 2 AAA batteries. Here's the adapter plate that I've made to get the Mosquito hot end here onto the Sherpa Mini, and it weighs 4 grams. So that is potentially, I would say 5 grams once you remove these 2 lugs that you could have eliminated by integrating just these 2 little screw holes into the Sherpa Mini itself. Fully assembled with the superior Mosquito hot end, this thing weighs in at 176 grams. The previous winner here with the V6 hot end and an aluminum block. So You're going to get less performance out of this compared to the copper block on the Mosquito. And this thing weighs in at 191 grams, so there's a 15 gram difference between the two. And the Orbiter has a gear ratio of 7.5 to 1, I believe, with the planetary gear set in there. This one has a 5 to 1 or a 50 to 8. I don't know which, though. There's two different versions. So one of those, basically it's 5 to 1, which means that theoretically this one is not going to perform as well because it's going to have less torque. So this is the box that the Sherpa Mini came in, and this is the box for the Orbiter extruder. And look at these boxes. They're identical. The cardboard is identical. The writing, the printing is in blue and black. The layout on the box, made in China dot bit, made in China Phi-set. Like, this is clearly made in the same place. China's supposed to be a really big country with all kinds of manufacturing, and yet they're using identical packaging, more or less. So they had their graphic designer change up the printing, but they're still using two-color printing. And yeah, I mean, this just supports my hypothesis that there is no such thing really as brand names in China. It's all coming out of the same factory, the same teams. They just sort of shuffle around the people who are doing the different teams for the different products. But it's fair. When I say China, I'm not talking about people. I'm talking about a place. I'm talking about one giant monolithic factory. I want to take this moment to talk about the difficulty of pulling filament out manually. So I've got the arm here that I can pull off and release the tension on the filament, but it doesn't quite release. It's still just the way that the tolerances are inside of the thing. It's really difficult to manually feed things through. And not only is it difficult to remove, it's also difficult to load. I mean, you can see here that I am opening the gate for sure. Slide it in until it's touching the hob gear. Open the gate. And I still can't get that in there. I need to sort of hold it on there with pressure and then use the extruder itself to load the filament. Not user-friendly in the slightest. So I was running the max extrusion test and I was getting some funny results. They were varying, they weren't very consistent. And then I touched the stepper motor and it was really hot. So I put the thermocouple, the K-type thermocouple on it, and it was measuring about 50 to 70 degrees. It was 50 degrees by the time I got the sensor out to measure it, but it was a lot warmer when I was touching it with my hands. So you can see right now it's at around 20, 30 degrees. So a little bit warmer than room temperature, but not too bad. And I've dialed down the milliamps of current being sent to the stepper motor to 500 milliamps. And that's, I think, going to be the kind of maximum. Although stepper motors are supposed to be reasonably tough. So I don't think I've done any damage to the stepper motor, but getting it that hot might have diminished the magnetic flux in there and diminished the torque of the stepper motor. So now that that's been fixed, let's do a max extrusion rate test starting at 250 millimeters per minute. We have a red line. You can just barely see it. It's mostly buried inside of the Bowden tube. And there is our next red mark. That is 100 millimeters between the marks. Let's see if we can get it to go 100 millimeters. Perfect. 400. We missed a few steps on that one. 350 millimeters per minute. Yeah, that's pretty good. 360. Yep, about a millimeter's lost. So 1 millimeter, and we're back to where we need to be, more or less. So I'm going to call it 350 millimeters per minute as the max. And that motor is, yeah, a little warm, but not uncomfortable to touch. 350 millimeters per minute. What does that mean? It means that as you're extruding 1.75 millimeter filament through here, you will start to get skips in your extrusion when you print above 175 millimeters per second in the XY travel. And most of us never print that fast to begin with, so this will be able to handle all of the printing that you're typically going to do on any normal machine. Of course, there are these speed racers doing the speedboat challenge, and they're exceeding those speeds for sure. I exceed those speeds on my Delta printer when I'm trying to get a quick draft print done just for testing, just the preliminary rough draft of a print of a design. So yeah, it does the job, and it's certainly going to limit ringing for a typical printer, but that stepper motor is not robust enough. Which brings us to the next question. Why did the Sherpa Mini here, with only a 5-to-1 gear reduction, outperform the Orbiter extruder with a 7.5-to-1 gear reduction when they both have the exact same stepper motor driving them? And the answer to that question is unknowable because there's too many variables at this moment. I used different hot ends. I used the copper block of the Mosquito hot end with the Sherpa Mini here, whereas the Orbiter was using just a Chinese aluminum block, so there's going to be different flow characteristics. Maybe the melt chamber is longer and the filament gets more evenly heated, so there's less friction in the filament path. With the Mosquito, we know this is a superior hot end, so really a lot of that performance could be explained by the hot end, but there's more to it than that. Of course, the Orbiter extruder with the planetary gear set has a lot more friction in the gearbox itself, so maybe that's where the loss is coming from. Or this is a big one too, and it's a big unknown, but maybe we're reaching that point where gains in torque that we get from the increased gear ratio, 7.5-to-1, are being lost by the decrease in torque because we're spinning the motor faster to drive the gearbox that fast. So yeah, that could be it too. Of course, we should eliminate variables, have these all printing through the same exact hot end, all these kinds of things if I'm doing science here, but I'm not. I'm just kind of seeing the best package that I can build, and the best package means the lightest weight with the most extruder performance, and there is a lot of smart science that went into designing the Mosquito hot end. It really is the best thing out there, and that's why I combined the best hot end that I have with the lightest weight extruder that I have currently seen. That's why I made this thing, and this is the thing that I was testing. And the final variable is the fact that I decreased the torque on this to 500 milliamps, where I was running the Orbiter at the full 800 milliamps, and it was getting toasty. And I was also getting those erratic, performance, but it was only erratic within, like, I would say plus or minus 25 millimeters per minute. So it wasn't that big of a deal, and I think that just getting the extruder up to 70 degrees meant that the magnetic flux was being interrupted at those high temperatures. But as soon as the temperatures cool back down, there's no lasting damage in these extruders. So I could certainly do science. I could certainly try to scientifically break it down, but guys, I don't think you're going to find that very interesting. I don't think it's a great use of my time, and every time I spend a bunch of effort to make a video like that, it doesn't perform any better than my typical videos. So I'll leave the engineering science to Stefan. He does a great job of it, and maybe this is a subject that he'll want to dive into. What I'm trying to accomplish on this channel is just a discussion about the design and the thinking that goes into all of these 3D printers and the components on the 3D printers. Speaking of the design, what would I change? Well, the number one thing I wish I could do is to bolt this Pancake NEMA 17 motor onto the back of the extruder here. Unfortunately, that's not an easy thing to accomplish. The gear, the main driving gear coming off of the extruder, is actually on a sized down axle. So the axle has been spun down, and it's much narrower in diameter versus the 5mm shaft that comes out of the NEMA 17. So to put a gear on the outside of this shaft, you're going to necessarily use a larger gear, which is going to reduce the 5-to-1 gear reduction probably to something like a 3-to-1, which is what we saw last time on the Superfly, that DIY project. So if I do something like this using a pancake stepper, probably only the best thing I can accomplish is the 3-to-1 by borrowing the gearing from the Bondtech BMG. What I really want is a 5-to-1 gear ratio, pancake stepper, as lightweight as the Sherpa with the Mosquito hot end on the thing. That's what I would create if I was going to make one of these. But there are some changes that I could make to the Sherpa Mini here, still using the same stepper motor. And The number one of those is to give a little bit more slop or a little bit more space around the filament path as it goes through the hob gears. And it's nice to have it as tight as this is. It means that flexible filaments aren't going to accidentally work their way out of the filament path. The floppiest filaments will be fed through the Sherpa Mini here. But in my experience, you can get a little bit sloppier than this and still have no problem with flexible filaments. And by being a little bit sloppier, I wouldn't experience those problems removing filament or installing filament by hand by pulling open the breech with this little door here. Not only that, but by giving more space to the filament path, I could then accomplish what was accomplished with the Superfly, and that is loading the entire gear from the backside, which would also allow me to drop 2 bolts from the assembly, as well as some plastic, thus making the thing even lighter. So small loss in filament path constraint for a larger gain in weight reduction and usability. And if I ever do this, which I don't know, chime in if you think this is something that's worth my time. But if I do it, I'm going to integrate the mounts for the Mosquito hot end as well. So it should be really compact and the lightest weight possible. But still, with this tiny little stepper motor, I really wish I could get a pancake on there. I just don't see an easy path to accomplish that task while maintaining the 5:1 gear ratio. All right, that'll do it for this video. Big thank you. As always, my Patreon supporters are the best. I love you guys. You keep me making videos. Yeah, you make it fun for me. You make me not want to quit. Speaking of supporters and all of that, I'm thinking of starting up a Discord channel, maybe. I'm getting a lot of requests from people to start a community, and I get it. I get it. Yeah, I mean, the comments section is a pretty lousy community, right? So it'd be nice if there was a place for everybody to sort of meet each other and to talk amongst, to talk amongst the crowd. It's not just me as the like filter. And I've always wanted this channel to be larger than just myself, which is part of the reason why I don't introduce myself on camera. So yeah, chime in the comments too or send me an email, or a Patreon message if that's something that you think I should be doing as well. So I would love to hear from you guys on that front. But yeah, thank you to the Patreon supporters. And with that, we're going to leave it there and say goodbye. See you next time. Thanks for watching.